Thanks to the organizers for inviting me. It's nice to be here and have this opportunity to give a couple of talks, but also it's been great to be here for a longer period of time. Just enjoy talking with people and the scenery. So I decided to give a mini course on this theory of two Segal objects. Most of the talk's going to focus on the simplest case of two Segal sets. With an eye towards accessibility, since I know we have a range of backgrounds in the audience. And my goal is to make some connections here. I think this is a theory that's relatively new and deserves to be better known. I'm going to talk about some connections with algebraic K theory and Hall algebra. That's going to be in the second talk this morning. So I hope that I can reach out to different people here and happy to talk further about this as the week goes on. If I can not to move.
Maybe you can click the slide.
Click the slide. Oh, there we go. Okay. Okay. So here's the big picture here. That one Segal objects, which maybe you've seen without a one in front, but I'm putting the one to contrast it. One Segal objects are things that behave like categories. So you have objects, you have morphisms between your objects, and then those morphisms have a composition that is associative, have identity morphisms for all your objects, things like this. Now, two Segal objects are going to be a little bit weaker. And so these are still going to have objects and morphisms, but now composition may not always exist. When it does exist, it may not be unique. But in a sensible way, it is still associative. And it also ends up to still be unital. I'm not going to focus so much on unitality here. So in particular, if you saw the two and you were thinking this was two categorical, that's actually not that's not the direction that this is. So, sorry, it's disappointing. Okay. So the goal for the first talk this morning is just to give precise definitions of these heuristic ideas and then give some examples. Okay, so I want to start with the underlying combinatorial framework. I know simplicial sets are very familiar to some people here, but maybe not to everybody. And it's critical to understand how these work for what follows. So a simplicial set. So if you're familiar with simplicial complexes, you can have that as a starting point. This is a collection of sets, Kn for every n, 0, and then we have a bunch of maps. And if it's hard to read, there are two maps going down from K1 to K0, one going up. And then, well, now from K2 to K1, there's three maps going down and two maps going up. And then downward maps are what are called faith maps. And again, if you're familiar with simplicial complexes, these hopefully match your intuition. But in simplicial sets, we have a directionality. These arrows are tiny, but they're arrows going from V0 to V1, V1 and V2, and V0 and V2. And the face maps, which are indexed by 0, 1, and 2, are given by deleting the vertex of that index. So if I take D0 of this two simplex sigma, I am basically covering up V0, and I just take the face opposite, which is E0. And then D1 is opposite V1. This is, if you think of eventually we're going to be thinking of these as sort of consecutive, like composable arrows. E1 is like a composite. That's what D1 is going to do. And then D2 is going to take the face opposite V2, which is E2. Okay. Now the upward arrows, these are the things that are maybe not familiar. If you've only thought about simplicial complexes, these are what are called degeneracy maps. And they enable us to take a simplex of a dimension and think of it as sort of an honorary simplex of a higher dimension. So if you have a one simplex F, as I've drawn here, then there are two degeneracy maps, ways of thinking of this as a degenerate two simplex. And basically we're saying we're going to sort of double it and make one of our faces of the two simplex just be well, what's a degenerate one simplex, which is coming from a zero simplex. So you can either put that sort of on the right side, so that your D0 is degenerate, that's the S1, and then S0, you're doubling up here this zero vertex. So those are kind of the way to think about those. So these space and degeneracy maps are going to pop up throughout. I make this little message go. Okay, now from a more categorical perspective, we think of a simplicial set as a function. So the category delta, this is the category of finite ordered sets. So bracket n is the ordered set with n plus 1 elements, start the indexing at 0. And for all, so we have that for all natural numbers n, and then we have order preserving functions between them. And if you're looking, again, it's probably hard for you to see the direction of the arrows. These are the reverse of the ones that we just saw. So we denote by delta op, the opposite category. So we have the same objects, we just formally reverse the direction of the arrows. And then we say that a simplicial set is a functor from this opposite category into the category of sets. And that, well, in some sense, it recovers the definition that we just had, that it's a collection of sets. This also nicely encodes the relations, the simplicial identities between those sets that I glossed over, that I didn't talk about because they're a pain from the other perspective, but they're packaged in the identity sets. All right, so for any n, there's a simplicial set that I write as delta bracket n, we call the n simplex. This is the representable simplicial set, so it's given by Homs in delta into that fixed n. So its set of case simplices will be all the maps in delta from k to n. Now, I realize there's people here who think more topologically than categorically or algebraically. So these can always be geometrically realized. So when I say, that I'm calling this the simplicial n simplex, if I geometrically realize it, and that's basically by saying, hey, this abstract set of zero simplices, think of them as points. These abstract one simplices, think of them as edges between those points, and so on and so forth. That's a geometric, you can make that more rigorous, that's a geometric realization functor. So you could think of these more topologically. The geometric realization of this simplicial n simplex is just going to be the usual topological n simplex. And so as a representable functor, familiar with this, then the Yoneda lemma is going to tell us that if we map this simplicial n simplex delta n into any k, then we get a set isomorphic to the set of n simplices. And that's going to be useful to remember in what follows. So conceptually, you're saying, hey, I have this thing that models an n simplex. I map it in, that's going to pick out my set of n simplices. I realize the word simplex is just being thrown around in all kinds of ways, but it's all standard. All right, so let's think about something algebraic, but from this point of view. So let's just pick a monoid. Now, in an algebra class, you would generally just say, hey, a monoid is a set, put for the binary operation, and it has an identity element, and it's associative, just no inverses. It may not be a group. And we can associate this monoid to a simplicial set. And so in level 0, we just have a single zero simplex. That's just the identity element by itself. We put the rest of m in dimension 1. And then we just take at level n, we put n copies of m, the product of m with itself n times. And now, well, our face maps from m down to e are just what they have to be. There aren't a lot of choices. That the degeneracy map is just going to include the identity element into m. And then, well, from m to m cross m, we just have the two inclusions into the factors. And then from m cross m, well, we've got two projections, but then we also have the multiplication. We have our binary operation, and that's where the algebra comes in. And if you keep going and you check some simplicial identities, this is going to tell you that you get associativity when you look up in in dimension 3. Okay, now we can do this more generally for any category. We say, well, a monoid alternatively is just a category with one object. We can take a more general category. We can say, all right, so the zero simplices are going to be the objects of C. Then we put the morphisms of C. Now our two face maps are more interesting. We have a source and a target. And then the degeneracy is going to pick out the identity morphism on that object. And then in dimension 2, so we have, these are going to be pairs of composable morphisms. So we say, all right, every time I have two morphisms, or the target of one is the source of the next, that's the agreement on the objects, we're going to fill that in with the two syntax, where the other face is just the composite. Okay, and so this is what's called the nerve. You can always then geometrically realize this to get a classifying space. Okay. So a question you might ask is, which simplicial sets are nerves of categories? If I hand you a simplicial set, how could you know if it came from a category in this way? And this motivates our definition of one Segal. So a one Segal set is a simplicial set K, such that these maps, which I'll say more about in a moment, these one Segal maps are isomorphisms. So these are going to go from Kn to K1, so an iterated pullback of K1s along K0s. So you should be thinking of this as something like, I mean, in the nerve of a category, this is what it looks like in dimension 2, well, and higher. I mean, the higher simplices in the nerve look like this. Oops, backwards, not forward. Okay, and so what you're thinking of on the right-hand side is you have a string of n composable arrows, and you're saying, well, I want to be able to complete that uniquely to an n simplex. And this is what's telling you, hey, this is coming from a category, it's encoding composition, finitely composition. Okay, so let me go into a little bit more detail about that. So for any n, at least 2, consider the inclusion. So Gn, I've drawn it schematically. You can write it as a colimit of a bunch of one simplices. So it's just a string of here. I mean, this is just a simplicial set. So we're just saying, hey, we have these zero simplices, we have one simplices between them, sort of n to n, and I can include that into an n simplex. Again, if n equals 2, you're thinking of this as sort of the little tent shaped figure and then including into the two. Okay. And now this is where this representability kicks in. So I have this map from Gn to delta n. Gn, by the way, is sometimes called the spine, if you've seen that notation. So if you map into a simplicial set, well, it's contravariant, so you get maps from delta n into k, and then you get maps from Gn into k. Well, we've already seen, Yoneda lemma tells us that from delta n into k is just the set of n simplices, Kn. And if you think about, what happens if I map Gn into k? Well, mapping any one of those arrows in is going to pick out a one simplex. And then, so I'm going to get a bunch of one simplices that agree, sort of target of one is source of the next. That's exactly this pullback. So this is where we got those Segal maps from in the definition of one Segal. So in particular, I mean, nothing I've done on this slide assumes anything. These maps exist always for any simplicial set. We're just saying, well, we're interested in when these maps are all isomorphisms. Okay, and in fact, this is exactly what characterizes nerves of categories. So a simplicial set is a one Segal set, if and only if it is the nerve of a category. And you might think a little bit about, all right, well, how would I run this backwards? So if I handed you a one Segal set according to the definition, how would you recover a category up to isomorphism? But you say, all right, well, K0, that should be my object set, K1 should be my morphism set, and if I want composition, well, if I take it, I know that if I take K2, the set of two simplices, that is isomorphic to this pullback of K1s along K0 via the maps D0 and D2. And, well, what's a composition? I need something in that pullback, a pair of morphisms that agree on an object, and I need to produce another morphism. So I can say, oh, well, run this isomorphism back and take D1. That gives me the opposite face of that two simplex. That's the composite. And the fact that this map is an isomorphism says, yes, there is actually a strictly defined composition. You really do get a category. The remaining thing you have to check is just identities. So I'll leave that to you if you want to check that this really has identity morphisms that behave properly. Okay, so I mean, you know, why do we want to do this? I mean, it seems like a simplicial set is kind of a big messy thing. Isn't the data just the nerve of a category? I mean, gosh, I haven't even really used anything higher than dimension 2. Well, okay, I also didn't verify associativity for you, which you need to go up to dimension 3, you know, for that. Okay, I'll leave that as an exercise. But you can say, gosh, I've got all these other things, this other information, and it seems kind of extraneous. But this gets really helpful when you want to work not discretely, as we have been with sets, but when we want to work more topologically. So rather than just taking simplicial sets, you could take functors from delta up into any category. I'm mainly here going to work with the category of simplicial sets. So these are simplicial objects in simplicial sets. If you'd rather think about simplicial objects in topological spaces, you can do that as well. And now we say, well, now we don't want to ask for these Segal maps to be isomorphisms. That would be very strict. We instead say, well, we want them to be weak homotopy equivalences. Where in simplicial sets, you say it's a weak equivalence if it geometrically realizes to a weak homotopy equivalence of spaces. And now we're doing everything up to homotopy. You say on one Segal space, so that's going to be such a functor. This has x0, which is a space of objects, x1, which is a space of morphisms. And now composition isn't strictly defined anymore. It's defined up to homotopy. We still have this Segal map being a weak equivalence. And well, if you put some other mild assumptions, maybe this map is a fibration, and so you have a section. Especially nice if you can do that. You say, all right, well, you get something up here. It's not completely unique, but it's unique up to say contractible space of choices, and then you push it forward, and that's your composition. So weaker notion, but it's still something that behaves a lot. All right, so that's your crash course in one Segal. So what is two Segal and where does the two come from if it's not higher categorical? So in defining one Segal, we use these objects GN, and so this was this string of arrows. And we can think of that as a kind of triangulation. So you had like a line segment, if you're thinking topologically, you had a line segment and you chopped it up into n sub-segments. And so we could say, well, what if you played that kind of game in a higher dimension where you did triangulation, say, of polygons, something two-dimensional? So the smallest non-trivial case is where you take a square. So I'm going to, so first of all, say, well, if you have a square, you've got two possible triangulations. I mean, here I only want to take triangulations with the vertices I have. I don't want to add any new vertices anywhere, but I can take either one diagonal or I can take the other diagonal. And I'm going to keep track of everything here. You'll notice there's a lot of decorations on these squares. So first of all, I labeled the vertices. So I've given them a cyclic ordering. from 0 up to, in this case, 3, going counterclockwise. And then I've also just sort of put the arrows which match the ordering on those numbers, and I've done that for the diagonals as well. So again, this is just bookkeeping. I can tell them apart, and it's going to be helpful in what follows. So if I call these T1 and T2, think of those triangles as being shaded. This is going to give two faces of the boundary of a three simplex. So, you know, the union of these two triangles, if you look at the indexing, this is going to give you the boundary of the three simplex. Just looks like a tetrahedron. All right, so we're going to do the same thing that we did with the one Segal maps. We're going to say, all right, I have these maps. I have these inclusions of T1 and T2 into a three simplex. And now let me just map those to a fixed simplicial set K. And I get these different maps. Now, again, when I map delta 3 into K, I get the set of three simplices. And now when I map either of these triangulations in, I'm going to get, well, each of these triangulations is going to pick out the data of two simplices that agree along on one simplex. But just using that notation doesn't distinguish them anymore because these are not the same pullback. So I put the maps here. If you go back and you say, well, where do these sit in the three simplex? So if I look, say, at this triangle from 0 to 1 to 2, that's the face of a three simplex where I've left off the vertex 3. So that's the D3 face map. If I look at the one from 0 to 2 to 1, that's D1. I left off the vertex 1, took the face opposite of that. And so that is just the ordered pair, D1, D3. And similarly, other triangulation is D0, D2. Okay, but it is just, you know, it is important that it's these two pairs. I mean, there are other, we could take other possible, you know, pairs or faces, but they don't, you know, they have to be these ones that come from the triangle. Okay. And this can be generalized. So if I take any n+1 gon, cyclically labeled vertices, put in diagonals to get a triangulation, this is going to induce a map from Kn to now n-1 triangles glued along common edges. So for something too Segal, we ask that these maps be isomorphisms. Again, I'm back to the discrete page here, I'm just doing sets. So a two Segal set is a simplicial set K such that for every n, now at least 3 is what we need for this to be interesting, together with any triangulation T of a regular n+1 gon with cyclically labeled vertices, the associated two Segal map is an isomorphism. So something you notice there's a lot. I mean, for one Segal, we have one map in each dimension. Now we have they're indexed by the Catalan, which index the number of triangulations. It turns out you don't need all of them, but I'm not going to get into that here so much. Okay, and similarly, so as just as we made the transition from one Segal sets to one Segal spaces, you can do the same thing here. So take functors from delta off into spaces and ask for all of these two Segal maps now to be homotopy equivalents or weak homotopy equivalents. So, all right, well, how should we think of this? If a one Segal set was the nerve of a category, what is this doing for us? Well, it should be something weaker. So we can still think of K0 as objects, K1 as morphisms, but now we're going to have trouble when we try to do composition because we don't know anything about this map from K2 to K1 cross K1 over K0 anymore. We know nothing about that map. So we say, well, we do the only thing we can possibly do, which is we take a pair on the left-hand side, we look at a pre-image of it in K2, if it exists, and then push it forward. And I didn't label them here, but it's still D0, D2, and D1. So if this map is not surjective, then you're gonna have things where composition doesn't exist. There's no pre-image, there's nothing you can do. But if this map is not injected, you can also get multiple possible compositions. So you have different pre-images, then you possibly get different compositions. However, when it makes sense to ask the question of associativity, this is associative. Let me go back to my triangulations. So if you think of going from 0 to 1 to 2 to 3, you think of this as a threefold composition. Say you've got an F and a G and an H, and that arrow from 0 to 3 should be sort of the composite of all of them. And this triangle is where you say, okay, take F and then G and compose them, and then compose with H, and then 0 to 3 should be the composite. Over here is where I make the other choice. They say, well, compose the G from 1 to 2 with the H from 2 to 3 to get that diagonal, and then you pre-compose that with F. But the fact that either one of these uniquely determine the same 3 simplex says that 0 to 3 has to be the same composite either way. And that's exactly what associativity is. So what the two Segal condition says is, okay, I can't tell you whether I have composition or not, but if I have if I have this configuration of 2 simplices, sort of, I already have some things that I know compose, have all this data, then it must satisfy associativity.
That seemed to contradict non-uniqueness.
Well, the thing is what if you're starting with this state? That's a great question, because what happens if this is non-unique? You're starting with the data of 2 simplices, which means you've chosen a composition. So if I'm looking at, say, the 0 to 1 to 2 and that diagonal is a chosen composition. There could be another configuration with a different composition, but I'm not worried about that right now. So you're already starting with the data of some composites existing. Well, you're basically assuming you have both these triangles who've chosen various composites, and they have to fit together nicely. So that's why associativity is weird, because you're saying, well, but you've sort of already been handed enough of the data, and associativity says they agree. Yeah. Takes a little bit. Okay. All right. So where did this all come from? So I've taken the approach here of Dyckerhoff and Kapranov. They're the ones that use the name 2 Segal, that sort of come at it from this notion of triangulations. But the same thing comes up in work of Galvez-Carrillo, Kock and Tonks. They have a different definition. They describe it differently. They call them decomposition. Well, so what we're calling a 2 Segal space, they would call it decomposition space. And the name is kind of coming from they're thinking of it not so much as, well, my composition may or may not exist. They're thinking of it more in terms of, hey, I have an arrow. What are the different ways I can decompose it? And they end up, so I'm putting a discrete here since I'm mainly talking about 2 Segal sets. There's a just be discrete. So I'm giving, sort of just one point of view here, but there's kind of this whole other way of getting at this. And, the motivations between the two are quite different. The second group of authors was really interested in doing homotopical versions of constructions in combinatorics. The first group, they were looking at things a little bit more geometric, connecting with representation theory, some things I'm going to talk about later, but as we'll see, both groups kind of stumble on some of the same key examples, which is kind of fascinating. It's kind of all happened at the same time, and different motivations, but they kind of end up in the same place. Okay, but we're overdue for some actual examples. So we talked about nerves of monoids. We can talk about partial monoids. So these are things people have done, Segal talked about these in work on configuration spaces. So a partial monoid, so we can think of as a set M, equipped sort of, well, with a partial multiplication. So you can't, you're thinking of a set with a binary operation, but the binary operation doesn't work for all pairs. So you say, let's take a subset M2 of the product of M with itself. These are the allowable pairs. So these are the things that you can multiply. And we put some conditions on this. We want associativity. So we sort of say, well, if I have, if it exists to take M multiplied with M prime and then multiply with M double prime, then I want the other way around, where I multiply M prime and M double prime first, and then I want them to be defined if and only if the other, and then they're equal. So I still want associativity. This is sort of the same sense in which we had it before. And then we need to have an identity element, and we want everything to be composable with the identity, and then behaves like an identity. Okay. So like an ordinary monoid, we can associate to this a simplicial set for a nerve type construction. In this case, it's maybe a little easier just to describe it just manually. So we're going to construct a simplicial set. We're going to let M0 just be a 1-point set. It's just the identity element. And then after that, we say we'll take M sub k. This will be a subset of the k-fold product of M. It's sort of the allowable k tuples that you can multiply. So these are k tuples such that if I take any string of length I and I multiply those together, and then I take mi plus 1, those are in M2. M2 is the thing that's sort of already predefined. So basically you want the tuples where the k-fold multiplication is going to make sense. It's going to be defined. And then just as in the ordinary nerve, base maps are given by, well, either projection for the outer faces or composition. And then the degeneracy maps are just given by insertion of the identity element into a slot. So this is a two Segal set. But it's not one Segal. Composition doesn't always exist. You actually have to be a monoid in the usual sense in order to be one Segal. But because we've built in associativity, and you can check this for the definition, but it's really easy. Okay, so for a more geometric example, so if you've seen a cobordism category, this is a variant of that. So I'm going to look at two-dimensional cobordisms, and what's going to make it two Segal is a genus constraint. So I'm going to say I only want cobordisms that have up to a certain fixed genus and no higher. Okay, so we're going to say the ones, I'm just going to go ahead and describe this straight as a simplicial set. So the zero simplices, these are going to be one-dimensional closed manifolds. So just collections of circles. And then, well, dimension 1, we're going to want cobordisms or diffeomorphism classes of cobordisms between those one-dimensional manifolds. And when we go to higher dimensions, we're going to say, all right, I'm going to think of a cobordism together with some decomposition into sort of cobordisms that are glued together. Okay, so, but some of these compositions are going to be allowable and some are not. So let's just take G equals 0. I only want cobordisms with 0 genus. Well, that says, here I have this sort of, three-legged pair of pants and a regular pair of pants and then these little caps, and that's fine. I can glue those three cobordisms together. I still don't get any genus. That's allowable. But this one is not, because I would create genus. So we would not permit this composition. And that's, okay, so we get something two Segal rather than this. Okay. But you might be a little bit unsatisfied with these examples, because in both cases, composition is unique if it exists. So in our partial monoid, we can't compose any two elements, but if we do, there's one answer. Same with the glue. I can either glue the cobordisms or I can't, but there's no, you know, there's no way to say, well, there's two different ways to do it. So in particular, this one Segal map that we use to get to define our composition, in these examples, it's always injective. And it need not be surjective, which is what makes it two Segal rather than one Segal, but it's always injective. So we want to look at an example where we actually have a multi-value composition. But it's a little bit more unknown. So these are going to be two Segal sets that come from graphs. So let's let G be a finite graph. So this is just a collection of vertices and edges. And we're going to associate to it a simplicial set that we'll call X sub G. Okay. So this is going to have a single zero simplex, which we'll denote by it has a single element, which we denote by the empty set. The set of one simplices will be all the subgraphs of G. And that's why, so the empty subgraph is the degenerate element. That's why we want to give that name to the single zero simplex. And then the set of n simplices will be, so we have a subgraph H of G, and then we have an ordered partition. I forgot the word ordered in this. So I have an ordered partition of the set of vertices into n disjoint, but possibly empty sets. So that's a little bit of a mouthful. So let's look at an example. So let's just look at this very small example of a graph. So we just have three vertices and two edges. And we're going to look at the associated two Segal set. Okay. So by definition, we have a single zero simplex given by the empty subgraph. And then these are all the ones. So these are all the subgraphs. So you have the singletons, you have sort of pairs, and well, if you're taking A, B, and B and BC, you can choose to have the edge between them or not. AC doesn't have an edge between it. So, and then you have the various subgraphs with all three vertices. You can see why I chose a very small graph. It blows up pretty quickly. Okay, so now two simplices. So these are things like, well, this thing up here where I have this subgraph that's A, B, and then C, and I just left off the edge between B and C. And I'm saying that, so my ordering here is that blue comes before orange. So, so I've partitioned, I put A in the first set in the partition, and then I put B and C into the second set in the partition. And the ordering is important so that I get a simplicial structure. I want to have base map. So if I have that two simplex, D0 is going to say, all right, take the first subset in the partition and throw it out. So I'm going to take that A and I'm just going to throw it out, and I'm only left with what's in the orange, which is just B and C. And then, well, edges come along or not, right? The partition is only on the vertices. The edges come along if they're included in the set, and they get thrown out if not. So that the fact that B was connected by an edge becomes irrelevant because the other end of that edge got thrown out. D2 is the opposite thing. So orange is the second set. We throw that out, we're just left with what's in the first set. And then D1 is a merge. So you just say, okay, take both sets, take their union, and you see in this case, we keep the edge. That was the okay, and then degeneracy maps are given by just inserting. Yeah.
A and B were required to be connected there. So
Here.
yes.
Right. So when we're starting with a subgraph with a partition of vertices, and you keep the edge whenever you keep both the vertices. But you see, when you did the D0, the D2, you only kept one of the vertices, so there's no way to keep that edge. But when you merge the two, you can keep the edge, because you didn't.
I can't remember the condition for, I can't remember the definition of two simplices, so,
Oh, okay. So a two simplex will have, so it'll be an H, S1, S2. So you'll have a subgraph together with an ordered partition of the vertices.
so any part is fine.
Yes, yes, and the partition can include empty subsets.
Everything composable then, this is sure.
This is just a graph so far. We're building a simplicial set we'll be able to do, but this is just, so this example that up here with the two colors. So our subgraph is just the A joined to B and then the C, that's the subgraph. And then the first set of the partition is just A, and the second set of the partition is B and C. Because remember, it's just a partition of vertices.
But then, you can compose edges when they are like disjoint. And compositions always seem to exist.
So are you talking about composition in the simplicial set that we're building?
Yeah.
I'm not there yet. I'm not there yet. Right now, I'm just trying to build the simplicial structure. So hold that thought, we're gonna get there, because that's what we want to talk about, but right now, I just want to say with the simplicial structure. Okay, so these are the phase, so this is how the phase maps work. Outer faces are chopping things off, inner faces are merging things. Okay. Degeneracies are going to be given by just inserting empty sets. So here's the one simplex. This is just the subgraph, and we're going to insert an empty set into its own set in the partition. If it says 0, we'll put the empty set first. Again, remember blue goes before orange. So the empty set will go first, and then the subgraph by itself. And then S1 will do the opposite. It'll keep the subgraph first and put the empty set second. Okay, so now let's talk about composition, right? So I presented this as it should be an example of something to Segal. So in this simplicial set that we've built, composition now is not unique. So here's an example. So we have two very similar subgraphs. So we have A and B without the edge between them. We also have A and B with the edge between them, each in their own set in the partition. But when I take this D0 and D2, I mean, that doesn't remember. The edge disappears if it exists. And so if I say, all right, I want a two simplex whose D0 is B and whose D2 is A. Well, it could have come from this two simplex without the edge, or it could have come from this two simplex with the edge. I have no way of remembering that. So both of those would be allowable. Two simplices. So and if you took the one simplex, the one face, the D1, so the D1 of this would just be A disjoint union B. The D1 of this would be, the graph with the edge between it. Those are both composites of B with A. So composition is not unique. It also doesn't always exist. So notice here, if I have, in order to be composable, in order for two one simplices to be composable, I need to have a two simplex such that D0 gives you one of the things and D2 gives you the other. That means they have to be disjoint, because D1 and D2 are just given by throwing the rest of the stuff away. So I can't compose subgraphs that are not disjoint from each other. So in particular, for both of these reasons, XG is not one Segal. And we see here that one Segal map is neither injective nor Segal. Does that answer your question? Okay. but I claim it is 2 Segal. And so I'm gonna give this by an illustration. So here's a diagram. So up in the upper left corner, this is a representative example of a 3 simplex. So I have a subgraph. I have A, B, C are joined, and now I have blue comes before orange, comes before green. That's my ordering on the partition. And I can say, well, let's look at the 2 Segal map that's given by D0, D2. So if I take D0, so that means throw out the first thing in the partition, which is A. Now notice the colors shift, orange becomes blue, you know, the indexing shifts. So I just get B and C. And then D2, okay, well, D2 is now from a 3 simplex is an interface map. That means merge the orange and the green. So merge the B and the C. Thus, so D2 gives you this 2 simplex over here. And now, all right, I have the D0, the D2, and I say, well, what's their common 1 simplex? Well, if you look back at that triangulation, take a D1 of this one and D0 of this one, and you do those maps, you get this same subgraph, just BC with the edge between them. So what 2 Segality is saying is if I just had the data of these two simplices glued together along this 1 simplex, could I uniquely reconstruct that 3 simplex? And the answer is yes. So, you know, basically you're saying, all right, up here in the upper right, I have the subgraph that I need. I just don't know where to put, you know, how to chop things up further into one more set in the partition. But this 2 simplex tells me how to do it. It says, oh, I need to split up the B and the C. So if you were just given this data, you could reconstruct that. And that's essentially what the 2 Segal condition is telling you. Okay, so I guess I went a little bit quickly. So that was what I wanted to do in the first talk. So just give you some formal definitions, give some examples. So I have another talk. And so in that talk, then I'm going to discuss 2 of the main applications. So one is the Waldhausen S-dot construction, which is really important in algebraic K-theory, and then Hall algebras. And as I mentioned earlier, we kind of had these 2 founders of the subject. And both of these applications seem in some sense fundamental because both sets of authors kind of stumbled upon them and recognized them as sort of fundamental to the theory. So even though I'm a little bit early, I think I will go ahead and stop here and take questions.
Thank you very much, Julie. Any questions or comments?
Yeah, can we go back to the CI with the square and showing that they associate with these? Yeah,
This one?
can we see this as a Cartesian square in some way physically? So can we reframe the 2 Segal condition to be some square of Cartesian?
Right, well, I mean, I think this is making a selective choice of, right, if you take the collection of all of them, let me try to write something over here. I know it's not super visible, but better than handwritten. I mean, so what you're doing is not great. So you have, oh no, this is, what's this will do? So I have Gosh, maybe you can read it, you want to read that. Let's see. I mean, this is, so. What this, if I have this map X3. To this pullback. You can like put these maps and things in. So if I look at the collection, all of these, and this map should be a pullback. That's what the two Segal condition says. I mean, here I'm picking an element. I'm just picking one element and saying what's happening just for illustration purposes. But the two Segal condition is saying this, when I take full sets here, this should be a pullback. But it's, for understanding what's going on, just gave a representative. Does that help?
Other questions or comments?
So I guess in algebra, sometimes there are weakenings of this, notion of a monoid or whatever, like
Yeah.
where you have associativity, but you don't have multiplication, but there's probably another weakening where you would have the multiplication, but not have associativity.
Yeah.
Is there any way to capture that using have you thought about that generalization?
No, I mean, in some sense, so what I did, if you go back and go all the way back to where I was. Actually, until this last bullet point, nothing that I said here used anything more than being a simplicial set. So like, you could just say, take any simplicial set, take any, potentially composable pair of one simplices, you can take the pre-image, you can define a composition. You just can't really say anything about it. So, two Segality is what says it's associative. So, so I guess if all you wanted was some kind of operation that need not, I guess if you. But yeah, I don't know, if you had a simplicial structure, I don't know how you would have like a uniquely defined composition without associativity. Yeah, I don't know. I guess, well, I suppose maybe you could just have this one Segal map be an isomorphism, but none of the higher one Segal maps. Maybe that would do it. Yeah, I don't.
Any more questions?
Yeah, in your coordinates category, you took diffeomorphism classes,
Yeah,
which is kind of designed to make composition unique, so you don't have to
Yeah.
choose colors and so on.
right.
What if you didn't do that? Would that still be one of your higher Segal things, or?
Yeah, so you could, you could do this sort of, in the regular cobordism category, right, you have where you take the diffeomorphism classes, which is like what I've done. Or you have like the higher version, which forms like a Segal space, where you say, oh, I have different choices for gluing, and so, I get like a space of compositions. So you could do the same thing here, and that would be the difference between getting like a two Segal set versus a two Segal space. I guess you would need, you'd need something where your like space of compositions is contractible or something in order for that to work, but yes, so like I was just trying to keep it simple, but yeah, you can, and probably in many cases would want to do that instead.
Any more questions? Maybe I have questions.
Yeah.
You can internalize this thing in other contexts. Is that what you're going to tell us in the next talk? What you do?
Internal.
Having two Segal facts, two Segal objects.
Right.
That
So,
would be next.
a bit. I'm basically only going to talk about two Segal spaces and a little bit about two Segal groupoids. But yeah, this makes sense. Take a sufficiently nice category with limits. Yeah. So you can do, so yeah, you can take two Segal objects in blank, where blank is just something sufficiently nice and basically you just need pullbacks.
There's
Yeah.
quite a lot of literature in the sort of early days of capitalism things internal to an algebraic category like groups and
Mhm.
numbers, and then you can usually think of it itself as an algebraic category. So I wonder,
Sure.
for example, if you take two Segal objects in groups, right, whether you can actually describe that itself as an algebraic category, and there could be interesting things coming out of that.
That's it,
Maybe
that's,
we can translate.
yeah, that's a really good question. I have not thought about examples of that type, but that would be
It's,
interesting. I mean,
The word.
yeah, right, right, yes.
Okay, any more questions? If not, let's thank you.